Triple integrals. A lot of students find triple integrals quite difficult, especially because the solids that we do integrals over are not very boxy. When they're boxy, the integral is not too bad. But when the bodies, the solids that we integrate over are not boxes or boxy, then the integration becomes much more difficult. The setup is more difficult. So these are big problems. So be aware of that. It is common that a problem takes half an hour. They're just big problems. So let's quickly go over these different integrals. In Calculus 1, we saw this kind of integrals over an interval. Usually we put a and b instead of an interval, but this, I just want to carry on the same kind of notation. So we got an interval. We're integrating over this interval, interval. Again, we usually put a and b. So we integrate from a to b. Right now I'm just using I for an interval, this particular interval, some kind of positive function. And so you guys are very familiar with this. In multivariable calculus, we saw this other integral, a double integral with respect to the area. We got a positive function. There is the region that we are integrating over, which happens to be a nice rectangle. So we go from A1, rather from A to B, and then from C to D. And you are familiar with this. Well, now move on. We move on to the next dimension. So this is one-dimensional function or input of the function. All of the functions are one-dimensional as far as the output goes. You know, the output is just going up. The output is going up. But the input is what changes. The dimension of the input is just one-dimensional. Here, the input is two-dimensional. And now we're going to see what happens when the input is three-dimensional. So the input here was this region on the floor. That's it. And then the output is graphed by this lines going up. Here, the input is, this is supposed to say box, B-O-X, box. The input is all of the box, all of it. The walls, the edges, the corners, and every single point inside of the box. So in order to draw the output, which is one-dimensional, we need 4 dimensions because the 3 dimensions are already taken by the 3 dimensions of the input. See, the input here requires 1 dimension. So we have plenty dimension to draw the output. Here, the input takes up 2 dimensions. So we have 1 more dimension because we can see things in 3 dimensions, but in 4 dimensions, I don't know how I can see it. But in 3 dimensions, we are able to. So we got 2 dimensions taken up by the input, and the output can be drawn because we got 3 dimensions. So 2 and 1 is 3. 1 and 1 is 2. So we still have a dimension left over. So this is easy to draw. This is drawable. I don't know how to draw this anymore. I really kind of need 2. This has to be thought abstractly. I don't know how to draw it because I need 4 dimensions to do this. You know, 3 dimensions are taken up by the input alone, and then the output is another dimension here. So I have to separate them and just kind of think abstractly, okay, and this point corresponds to this output maybe, and a point up here corresponds to an output here, and this point corresponds maybe to this output, you know, and you dance around the outputs. So the inputs are here, and then the outputs are there, and I just have to sort of make a table where the inputs are here and the outputs are there. While the advantage of graphing this function, we have the inputs here, and then the corresponding output is up there. So the 2 of them fit. There may be some overlapping, and there's some angles have to be drawn carefully so that The lines don't seem to be vertical when they're actually not. Here, this is the easiest one because every input has its corresponding output, and it's very easy to see, okay, this output corresponds to this input and so forth. This is the most difficult to see because we need 4 dimensions. So just be aware that's what we are doing. And what this boils down to is to multiply little bits of volume by corresponding outputs. Volumes and outputs. Volumes and outputs. Now, Fubini's theorem says that triple integral over a box of a function with respect to the volume is equal to iterated integrals, so one integral nested inside of the other of the same function, of course, dx, dy, dz, where x goes from, say, a1 to a2, y goes from b1 to b2, and z goes from c1 to c2. So usually we go from A to B, B to C, but then if I go on the same order, we're going to have E to F, and then we're starting bumping into the F we already have for the output of the function or for the name of the function. So instead of using from A to B, B to C, C and D to E, rather from A to B, B to C, rather C to D. See, I'm getting already confused. So instead of doing that, I'm just going to use A, B, and C, A1 and A2, B1 and B2, and C1 and C2. And what I mean by that is this. So you got your box, all right? So the x's are going to go from A1 to A2. The y's are going to go from B1 to B2. And then the z's are going to go from so the z's go from C1 up to C2. Yeah. So just be aware that's what we're going. X, Y, and then Z. Yep. And when we have a box, we can exchange those as long as we exchange those accordingly. So if you put the Y first, then the B's have to go more on the inside. And if you put the X way out, then the A's have to go out. Whatever numbers correspond to X have to correspond to the symbol in the integral. If you have fixed numbers, that is not too much of an issue. Before we start doing an example, let me first tell you that examples can be rather long, very, very long, and that is normal. Sometimes they are so complicated that what we do is integrate functions that are very simple. So if you see a function x, y, z that has just an x in it, and that's it, nothing else, then don't panic. What we are doing is integrating a function that is simple enough, because the integrating 3 times, as you will see in one of the examples at least, is going to get so cumbersome, so complicated. Even this simple function can be difficult to do. So what this means is that all you're going to pay attention to is the x, and the y and z are not relevant for purposes of the output of this function. So this is a very, very simple function. And even this simple function can get very complicated when we do a triple integral, extremely complicated. As I was preparing for this video, I actually had something quite simple, in my opinion, initially, X, Y, Z. And the paperwork for doing this was so long, and it was pages and pages and pages before I quit. And I said, no, that function is way too complicated. If I want to involve the three, we probably want to add, and that's going to make things a little simpler. Multiplying variables within one function for purposes of the integral gets really complicated very quickly. So just be aware that if you have something very simple, don't panic. There's nothing wrong. It's just that otherwise, if we put something like this, things get out of hand. And of course, um, if you have X, Y, Z, and a constant, say, I don't know, 11, that's an 11, then again, that's just a constant. We're integrating a constant. And the reason why we might want to do that is because either we're going to find a volume or something related to a volume, or we just want to keep things very, very simple. So these are just some examples, because we haven't done many examples of functions with three variables. Okay. All right. For the actual definition of a triple integral, you have to, of course, do limits of triple sums. I don't want to get too much into that because many of the books available, many of the textbooks have the definition. They are pretty well written. I want to supplement that with what I'm showing you. So you have to see videos along with reading the book. I'm giving you perhaps my perspective, but I don't want to reproduce what textbooks necessarily, all the textbooks do with, and I'm not saying they're not doing a good job. They're doing an excellent job. Definitions, they write definitions formally and so forth. But I just want to move on with examples and general ideas. So let's do examples. The first example, example 1 for this, we want to find the triple integral of, see, this is already a bit complicated, 4x plus 5y plus 6z with respect to z, y, and x respectively, as z goes from 0 to 3, y goes from 0 to 2, and x goes from 0 to 1. So this tells us that we are integrating over a box, and the box is 1 unit on the x direction, 2 units on the y direction, and then 3 units on the z direction. So if we extend that and form this parallelogram, so again, this is 1, 2, 2, and then we're going to go up to 3. So this is the box we're integrating over. In the x direction, we go 1 unit. In the y direction, we go 2 units. In the z direction, we go 3 units. So we're integrating over this box a function that I cannot draw in this picture because the function, the output of the function is in a 4th dimension. I already used up 3 dimensions just to draw the box. So I need another dimension. So this is, I don't know how to correlate it in one picture anymore. So we got outputs. The smallest output will be here when we, assuming that this is the origin of the x, y, and z axis. So because we start with 0, 0, 0, the smallest output is going to be here at 0. So pretend this is 0. Of course, we got negative numbers going down, but we're not going to use those because all of this is positive, all of the inputs we are using are positive, so there's no negatives involved. And the maximum is going to be probably out here. This vertex of the cube has coordinates 1, actually 1, 2, 3. So this vertex has coordinates 1, 2, 3. And when we plug in 1, 2, 3 into this, we get 4 times 1 plus 5 times 2 plus 6 times 3. And that would be the highest output we obtain. So that is going to be 14 and 18, 32, if I'm not mistaken. And we're going to get all the outputs in between by moving around. But we're going to get it more than once. You can get, for instance, I don't necessarily want to do the math, but you can get well, not 0 and not 32, but probably all the other outputs you can get more than once. So how do we go about computing this? Okay, we're gonna, these are iterated integrals. So we're gonna integrate with respect to z first. If you change the order, because we have fixed numbers up here and fixed numbers there, that is not a problem. However, the process will be different. We're gonna get to the same final answer, but we have to take different paths to get to that answer if we change the order of integration. If we change the order of integration, as I have mentioned earlier, we have to also change the order of the integrals. So let's go ahead with this computation. Within reason, this is a little bit of routine, but routine doesn't mean that it is not easy. You know, moving boxes it's a routine kind of work, but that is not easy. That's one of the examples I like to give. Anyway, so this is a constant with respect to z, constant with respect to z. Oh, there is z. So this varies with respect to z, but those two don't vary. So that means when we integrate with respect to z, we're going to end up with 4xz going from 0 to 3. So we're going to have 4x3 minus 4x0. I'm going to do that all in one shot. So we end up with 12x. Same thing here, 4yz, because this is a constant, as z goes from 0 to 3. So we end up with 4y3 minus, oh, I'm sorry, I didn't mean 4, 5. 5y3 minus 5y0. So the 3 and the 5 make 15 plus 15y. Here's where things get a little more messy. Because when this z is varying, and so the integration by using the fundamental theorem of calculus, we have to do the antiderivative first, 6z squared over 2. So remember, 6z squared over 2. The 6 and the 2 simplify down to 3. So we really have 3z squared from 0 to 3. So we end up with 3 times 9, 27. And then we have dy dx to do. Dy dx. Okay. So now we are integrating. We have a double integral, which we already know how to do from using from previous videos. All right, we're integrating with respect to y. So x is constant. So when we integrate this using the fundamental theorem of calculus, we're going to end up with 12xy as y goes from 0 to 2. So that's going to be 24x plus 15y. Oh, but we're integrating with respect to y. So this is going to be 15y squared over 2. 15y squared over 2 from 0 to 2. Well, we're going to end up with 4 on the numerator, of the y squared over 2. but then 4 divided by 2 is 2, so we end up with 30. Plus 27y, 27 is a constant, so what we attach y to it when we do the antiderivative, plug in 0, plug in 2, subtract the 1 with the 2 minus the 1 with the 0. So we really end up with 54 dx. And now this is a calculus 1 kind of integral. So we have 24x squared over 2, but we're going to plug in 1 and 0. So that's going to be half. When we plug in 1 into the x squared over 2, we're going to have a half times 24 is 12. And those two we should consolidate even before we do the integral. That is actually 84, a number. When we integrate, we're going to end up with 84x from 0 to 1. So that is going to be 84. And the total is 96. So the triple integral of this function, 4x plus 5y plus 6z, over this 96, over this box, will give us 96. What does that mean? Well, what is the volume of the box? Because after all, a triple integral is the same thing as the volume. One thing I missed to mention when I was talking about Fubini's theorem, this is true. Sorry to interrupt the example or the end of the example. This is true if the function is continuous. If the function is not continuous, then we don't necessarily know whether that is true, that a triple integral is equal to iterated integrals. So anyway, here, what does that mean? What is the volume of this box? Well, it is 6, correct? 1 by 2 by 3 is 6. So the volume is equal to 6. And the lowest output of the function is 0. The highest output is 32. What's in the middle? 16. So what we are doing, if you multiply the volume times the average output of the function, which in this case would be 16. So average output of f equals 16. Right in between 0 and 32, we get 16. Then if we multiply those two together, sure enough, we get 96. So one way to think of this, which is to think of the triple integral as the volume times the average output. But this average output is tricky to view, because this function is very linear, is very, very proportional, and the square, the cube, the box is also very boxy. It's, whatever you go one way, it comes the other way very evenly. So the average works really well when you have this linear function and a very, very nice even box. Most of the time, things are not going to work that nicely. And that's why we need the integral. Yeah. In fact, if things were this linear, if functions were this linear, and these solids were that simple, then we would not need triple integrals. All we have to do is a simple multiplication, 16 times 6, and that would give us 96. But most of the time, that is not going to be the case. Yep. So let's do an example that is more complicated. Okay. In my opinion, much more complicated. And this is one of the easy examples. Example 2. Take the tetrahedron, this tetrahedron, 2 units one way, so 2, 3 units the other way, and then 5 units up. this is a solid tetrahedron, so we don't only mean the plane, 2, 3, 5. We don't only mean the plane, but from this coordinate out to the plane, from this coordinate to the plane in every direction on the first octant. So all of the inputs, all of the x's, y's, and z's are positive. That's what we mean by first octant. And we're going to integrate over this solid. Now, this solid is not as nice as example 1 that was a nice box. It does help to know the equations of the surfaces. So the equation of the bottom surface is going to be z equals 0. The equation of this surface, I'm going to write it. The plane that is inclined is going to be 15x plus 10y plus 6z equals 30. So that is the plane. The back wall will be x equals 0. The left wall is y equals 0. And then that is the plane. Yep. And what are we going to integrate? We're going to integrate a very simple function, just x, which seems too simple. Somebody may say, well, that's why not xy or sine of x? Believe me, it gets really, really crazy very quickly. So this is the function, and this is the solid we're going to integrate over. We're going to label that as E. So we want to evaluate the triple integral over E of just x with respect to the volume. X is a nice continuous function, so we can use Frobenius theorem to rewrite this as a triple integral. Okay, so let's do that. 1, 2, 3, x. We're going to integrate with respect to z, so x is our function, then with respect to y, and then finally with respect to x. And there's a method I use to figure this out. So the z, the bottom z is 0. The upper z is, well, pretend you have a particle that is floating inside of this tetrahedron. It's just floating, or a spaceship. And you are just kind of navigating around this solid. If you start and at any point going down, you're going to bump into this plane on the bottom, z equals 0. And we're integrating with respect to z first. If you start navigating and going up, what are you going to bump into? What are you going to crash against? What is going to be your ceiling? And the ceiling is going to be this plane. So we got to solve this plane for z, and that's going to give us the upmost z inside this tetrahedron. So this is the lowest z value we will obtain, and the upmost is given by this tetrahedron. So the upmost for a z value, we have to solve this equation for z. And well, it starts out with 5. And then we got to take away 5 over 2 in the x direction. And then we got to take away 5 over 3 in the y direction. So this is this big thing is the upper limit of the first integral. See how difficult it starts getting already? Okay. Once the z is taken care of, then project this tetrahedron down to the xy plane. So I'm going to draw that here. Project the tetrahedron down to the xy plane, and that's going to project down to this triangle on the floor. So we're going to have 2 and 3. 2 and 3, 2 and 3. This is the x-axis, that is the y-axis. X goes to 2, y goes to 3. What is the equation of this? So we would like a 6 as an output. And we want x, so 3x plus 2y. So this is the equation of this side. Again, we're projecting everything down to the floor. So if we want to go on the y's, now again, pretend you are on a spaceship, but now this is not a solid, this is just a plane figure. It's a triangle. Still, if you go down to the floor, you end up with y equals 0. Remember, this line has equation y equals 0. And if you go up, we bump into this. So 0 for the y's. We're integrating next with respect to y. And we want to have a ceiling for y. So we solve this equation for y, and that gives us 3, because we're going to divide by 2, 3 minus 3x over 2. 3 minus 3, 3 halves of x. Again, 3 minus 3x, but then we're going to divide by 2. Okay, so how did I obtain this triangle? If we're integrating with respect to z, figure that out, the limits on z, then project this tetrahedron down to the xy plane because z is gone, z is taken care of. We end up with this triangle. Next, we're integrating with respect to y. So we go from 0 to, well, we figure out the equation of this diagonal, and then we realize we integrate from 0 to the y value for this diagonal, and that's it. Then we integrated with respect to y. So y is gone after that integration. Project this triangle down to the x-axis. So if you only have the x-axis, if we project this down to that, we're just going to obtain an interval, this interval. And the interval goes from 0 to 2. From 0 to 2. So the way I think of it is you have a tetrahedron, smash it down to the floor, you end up with this triangle. Once the y is taken care of, squish this down to the floor, which is going to be this segment from 0 to 2, and there we have it. We must have constants on our most outer interval. We cannot end up with variables. If you end up with variables on your most outer interval, something is really bad, is wrong. And it's a big mistake because that would mean that we don't know how to even set up an interval. So setting up an interval is not easy, and it is easy to get it wrong. Getting it wrong would not always, but many times may mean that the concept is not right, especially if we have variables in our most outer integral. We cannot have variables there because we're finishing up with a number there. Here, the only variable allowed in this limit is the x, because after finishing this up, the only thing left is x. Here we can have any variables, but we cannot have z's on the upper limit or lower limit. We cannot have z's because we're integrating with respect to z. We may have z's in the function, but not on the limits. So there's a lot going on here. Okay, so we're integrating x with respect to z initially, which means we're going to do xz. We're going to plug in this upper limit, and then we're going to plug in 0, and we're going to subtract. So by the time we do all of that, we're going to end up with x times that. I'm going to write that down. So we have the integral from 0 to 2 over the integral from 0 to 3 minus 3 over 2x. And we're going to have xz, but z takes this value, and we're going to subtract. Of course, with 0, we're going to end up with 0. So we have x times 5 minus 5 over 2x. minus 5 over 3y, close the parenthesis. That takes care of integration with respect to z. We still have to integrate with respect to y and with respect to x. I am pulling a fast one on the watchers of this video, but I did that here too. When we went from here to here, in example 1, I did pull a fast one because I said, well, this is 12. When we integrate with respect to, well, let me move to this one. When we integrate with respect to y, we did y squared over 2. Oh, this is a little confusing because we got 24. We get double this, but notice that there's no y because we're integrating with respect to y. So don't think it's just double that. I'm plugging in y squared over 2. What happens is that we plug in 2 and 0. So that's 2 squared over 2, which is 4 over 2, which is 2. 2 times 15 is 30, and that's how we obtain this 30. So I did pull a fast one here because I'm skipping the step of antiderivative, plugging in the 2, plugging in the 0 to obtain this. I'm doing exactly the same thing in this example. I did pull a fast one on you because I did xz, which is the antiderivative because x is a constant, and we're integrating with respect to z. Plug this in, plug 0 in, subtract, of course. So we end up with x times this, which is that. Before we continue integrating, we cannot integrate a product of variable inputs. Then again, we're integrating with respect to y. So x is a constant with respect to y. Watch out, because that is not always the case. So that means we can factor out 5 and the x from the first integral, not from the second integral. Watch out. Factoring the incorrect thing from an integral is a severe mistake. Many points are lost. It's not a minor mistake. It's a major mistake because that is a conceptual mistake. It is not good. 0, 2. We can factor out the 5, certainly, no matter what. We factor out the x from the first integral because the first integral in this double integral, in this iterated integral, because that is an integral with respect to y. We may never, ever factor the x out of this other integral because that is an integral with respect to x. All right, so we have the integral still 0, 3 minus 3 over 2 x. We did factor the x and the 5, so we end up with 1 minus half x minus a third y, dy dx. So, okay. 0, 2, 5x. All right, here's where I'm going to start pulling a fast one on people who are watching the video. Okay, so integrate 1, well, that's just y. But plug in this, subtract, and we end up with 3 minus 3 over 2x. Okay, that takes care of the 1. Minus half x, because we're integrating with respect to y, that means just y. Plug in this, plug in it, and subtract. So 3 minus 3 over 2x. Close parenthesis. Minus 1/3. Now, we are integrating with respect to y. So this is going to be y squared over 2. And we're going to plug in this, plug in that. 3 minus 3 over 2 squared over 2. That's because we are plugging that into the y squared over 2. Close the bracket. We still are integrating with respect to x. See how difficult this is getting? Even though I'm not necessarily skipping, but I'm doing some steps fastly than what I could. Okay, and there's more to that. So the 5x is multiplying all of this. We should simplify that before we even um, multiply by the x. The 5 is not, doesn't have to go in. The 5 is a constant with respect to x, so the 5 may factor out. Let's continue on a new sheet of paper. So this is 3. Sometimes I keep track of my pages. So this is 5 integral from 0 to 2 x. So in the previous page, I said I was going to factor the 5. The x may not factor out. That is a sin, a big one. There is no come back from that one. And then 3 minus 3 over 2x. 3 minus 3 over 2. I don't mean disrespect when I say sin. I mean a mathematical sin, of course, not a real sin. So then we have minus half x times 3. So that is going to be negative 3 over 2x minus 3 over 2x. And then we have a double negative. So that is plus 3 over 4 x squared plus 3 over 4, negative and negative. 1 times 3 is 3, 2 times 2 is 4, x times x, x squared. Okay. Minus 1/6, minus 1/6. And then we have to FOIL that out. 9 minus double this times that. So that is going to be 9 over 2, but double that. So that's just 9. 9. I did miss an x here. So x plus 9 over 4x squared. Close parenthesis, close the bracket. Don't forget your differential. Okay. So equals, I wanted to factor out the 3, but I can't because we should simplify this first. 5 integral from 0 to 2 x bracket 3 minus, well, those two together make a 3x plus 3 over 4 x squared. And now let's simplify this or multiply out. So we have 9 over 6, which is really 3 halves, minus 3 over 2 plus, because we have a negative times a negative, again, 3 halves. And then minus 3 halves, but then there's an extra 4. So that makes 3/8. X squared, close the bracket, dx. Okay. Equals 5, 0, 2, x. Let's simplify this before we multiply by the x. So 3 minus 3 halves. 3 minus 3 halves, well, that is 3 halves. That takes care of those two. 3x negative plus 3x, well, 3 over 2x. That makes negative 3 over 2x. And then we subtract those two, but this happens to be exactly half of that, so we end up with plus 3 over 8 x squared, close the bracket, dx. It's nice when, you know, this expands to two lines, and then back to one line. Multiply the x. I'm going to do two things. I'm going to multiply the x in, but I'm going to factor the 3 out at the same time. 15 integral from 0 to 2 of half x minus half x squared plus 1/8 of x cubed. Equals 15 times half. Well, that's going to be x squared over 2, but we're going to plug in 2 and 0. So 2 squared over 2 minus half, same thinking, 2 cubed over 3 plus 1/8 2 to the 4 over 4. And so 4 divided by 4 is 1 minus 1, 2 is out, so we end up with 4/3 plus that's 32, the top is 16, so we end up with a half. Common denominator will be 6, 15, 6 over 6, that's the 1, minus 8 over 6, plus 3 over 6. So that makes 9 over 6. The 1, 3 cancels with another 3 here. So we end up with 5 times 9 over 2. Wait a minute. Why did I say 9? 6 times 6 plus 3 is 9, but then we got to subtract the 8. So this is a 1. So the final answer is 5 over 2. So that is the integral of just the x over this tetrahedron, the x value. Now, the volume of the tetrahedron is 10. I'll explain that in a moment. But the volume is 10. So one might ask, well, the integral is 2.5, which is a lot less than 10. You know, in example 1, we got a lot more than the volume. The volume was 6, and we got 96 for the output. The reason is, in this case, because the average is 16. So here the x average is very small. In order to reduce the volume to 2.5, from 10 to 2.5, and I'm not saying that the volume got reduced. What I'm saying is that the triple integral is a lot less than the volume, which means that the output of the function is rather small, smaller than 1. Now, x goes from 1 to 2. And we're doing some kind of average. But think about this. Pretend you got little ping pong balls. And you just fill this with ping pong balls. The whole tetrahedron, ping pong balls all over. So you got, I don't know how many, hundreds, maybe thousands. Pretend those are 2 meters, 3 meters, 5 meters, which is gigantic. And then you got tons of ping pong ball inside. And then the question is, well, what is the x value for a ping pong ball? The first ping pong ball here, pretend if the x value is on the center of the ping pong ball. Well, that would be very, very little, you know, like 0.01. You know, a ping pong ball is like, I don't know, a few centimeters in diameter. So the center is maybe 1 or 2 centimeters. So that would be, if we were doing meters, 0.02. And then the next ping pong ball towards us would have the center would have an x coordinate of maybe 0.06 or something like that, assuming that the ping pong ball is 4 centimeters. Actually, I should check. I don't know the diameter. But what we would understand, or what we would notice, is that there's many ping pong balls against that wall, against this wall, too. But so we go from 0 to 1. This is 1. There's going to be, where we're concerned with is the x value. So there's going to be many, and by far many more ping pong balls that have an x value that is less than 1. than the ping pong balls that have an X value past 1. So in fact, we can sort of draw. Yeah. So past 1, we'll have this many. Before 1, we have this. So we have way, way many more X values that are going to be less than 1. And that's why the average gets to be small in comparing with the volume. The volume is 10. The volume of this tetrahedron is 10. Yet when we integrate the X, which takes into account the X value of the little inputs, and the little inputs in this case would be the little ping pong balls. When we take that into account, then a lot of those values are going to be less than 1. Many, many of them are going to be a third and even smaller than that. And that's why we obtain on the total a lot less than 1. And that's why we go from a volume of 10 to a triple integral of 2.5. Yeah. In our first example, are there many values that are going to be less than 1? 1 is going to be somewhere down here. Yeah, there's going to be some down close to the origin. But notice that there's going to be many, many values above 1. And that's why we have a multiplier of the volume. So what we are doing is multiplying the volume by the average. Well, I shouldn't say the average, by the output. But there's many outputs. So by the output that, I don't want to say that occurs the most, but the output that happens a lot. That's a very, very vague way to say that is not even correct, because we do multiply by every output, but many of the outputs are going to be less than 1, and that's why we reduce the 10 down. So that's one interpretation of this triple integral. Very, very, very quickly, I just want to say how to find the volume of a generic pyramid. To me, a pyramid has a flat face, doesn't matter what it is. It has a point, and then the side of the pyramid is made up by segments that join, straight segments that join the edge of the flat face, which is the base. So for instance, if we have, again, a pyramid would look like, whoops, like this. And this would be inside. So this is a generic pyramid. The height of a pyramid is taken from here to the floor, from the tip to the floor. The vertical distance is what we call the height. Label A as the area of the base. And the volume of such pyramid, a generic pyramid, is the area of the base times the height divided by 3. Yeah, and this is the pyramid doesn't have to be that straight. You can have a pyramid that is oblique, like that. The height still is the distance from the top to the extension of the floor. So the same formula works for this oblique pyramid, very oblique pyramid. So the reason why I bring that up is because I did mention that this is the volume of this is 10. Why? How do I come up with that? Well, look at the area of the base. The area of the base is 2 by 3, 6, divided by 2 because we got a triangle. So the area of this base is 3. Again, 2 by 3 is 6, divided by 2 because we have a triangle. And so that's 3 multiplied with 5. Whoa, I lied. 3 multiplied by 5, and that's going to give us 15. Whoa, so I was wrong here. The volume is not 10. Yeah, So 3 by 5 is 15. Half of that is 7.5. The volume is 7.5. Yeah. Yeah, not 10, 7.5 cubic units. Yeah. Good thing I corrected that in this video. All right. Changing the order of integration, iterated integrals, is not easy. Yeah, and that is the next thing we want to address. Changing order of integration. Not easy at all. So let's draw the same tetrahedron. 2, 3, 5. 2, 3, 5. 2 on the x's, 3 on the y's, 5 on the z's. There is 4 sides to this tetrahedron. The bottom, which is z equal to 0. The back wall, which is x equal to 0. The side wall on our left, which is y equal to 0. And then the plane, the inclined plane itself, which is 15x plus 10y plus 6z equal to 30. So plane, 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 4 planes, if they intersect correctly, form a tetrahedron. And that, in this case, 3 of the sides are 90, are perpendicular, so that makes the tetrahedron nice to work on. Okay, if you have a generic function f, so I'm just going to label it as f. It is understood that f is a function of 3 variables. In how many ways can we set up iterated integrals to find the integral of this function with respect to this tetrahedron or over this tetrahedron? And it turns out that there are 6 different ways to set it up. We are always going to end up with the same answer. The answer is going to be 5 over 2 because we did that in example 2. Oh, wait a minute. It is the same answer if we have the same function, but right now we are dealing with a generic function. If f was x, as in example 2, then no matter which combination of we use, which one of the 6 possible ways to set it up, we should end up with the same answer. So I'm going to focus now on how we set up integrals. So we have one that we already worked on. So the triple integral over this tetrahedron, let's call it big T for tetrahedron, over the tetrahedron, of a generic function f with respect to the volume. This can be done in six different ways. One is the integral from 0 to 2 on the axis, from 0 to 3 minus 3 over 2x on the y's, from 0 to 5 minus 5 over 2x minus 5 over 3y on the z's of the function, well, not just as well, x, y, z, dz, dy, dx. Now, if those were just fixed numbers, moving those 2 around and moving the corresponding integrals on the left is no problem if we have fixed numbers. But if we don't have fixed numbers, as is in this case, then moving them is a big deal. Okay, so let's move the y and the x. I'm sorry, I didn't mean that. Let's move the z and the y. Those 2 around, those 2 around. So we're going to still integrate eventually x from 0 to 2. X can only go from 0 to 2. So that is not going to change. But those 2 upper limits will change. So we have to analyze how how we go about it. So if we integrate, let me write the second integral here. There's going to be 0, blank, 0, bigger blank, f of x, y, z, dy, dz, dx. There are 6 different ways to rearrange dz, dy, dx. One of them is dz, dy, dx. Another one is dy, dz, dx. And there are 4 more to go after this one. Okay. So y, if you are a spaceship here and you move in the y direction, then the lowest you can go is 0 and the highest is the wall. But then we got to solve this equation for y. And that is going to give us 3 minus, if we solve this equation for y, 3 over 2 x minus 3 over 5. It's easier for me to observe that from the y perspective and the z perspective, the slope is rise over run. Yeah, that's okay. When you're in space, what is up and what is down? Well, that is totally relative. Up and down is whatever you wanted it to be. Whatever your feet are in space, if you're floating in space, you know, wherever your feet are, that's down. And you can be, you know, yeah. So what is down on this pen? Well, it's down here. But if it's the pen is floating in space, you know, that's down. You know, you define down whatever you wanted it to be. Traditionally, slope is rise over run. Yeah, but rise carries the concept of up and run forward. But again, what is up and what is forward is relative. So from the y perspective and the z perspective, let's see, I want to make sure. Yeah, the rise of y is 3 and the run with respect to z is 5. So the slope among y and z is going to be 3 over 5. That works for planes of that kind. So 3 over 5 z. Yep. So when z is 0, y is 3. So this is y, a y value. Yep. And x is 0 too. All right. So that's how we obtain, the bottom line is take the surface, whatever it is, solve for y, simplify, that's your upper limit if you're integrating with respect to y. Yeah, I should have started with that, perhaps. Then flatten the figure so that y is not there anymore. So that means flatten, squish this way against this wall. So we're going to have this triangle, 2 on the x's, 5 on the z's. So I'm going to draw that triangle, 2 on the x's, 2, and then 5 on the z's. So we have this. What is the equation of this line with respect to z and x? Now we are, oops, sorry, I didn't. So 2 on the x's, 5 on the z's. What is the equation of this line? So 2 times 5 is 10. We need a 10. And then we need a 2 when z is 0. So we need 5x to make the 2 plus, and we need a 2z. So 5x plus 2z equals 10 is the equation of this line. Okay. And if you're in a spaceship here and you're going in the z direction, you're going to bump into this diagonal and down here with a z of 0. Z of 0 The upper limit is going to be a z value. Yep, because we're integrating with respect to z, corresponding to this equation. So we need to solve this equation for z. And that's going to give us, divide by 2, so 5 5 minus boy, 5 over 2. 5 over 2x. So when x is 0, you get 5. When x is 2, you get 0. So that works. So this is the setup. If you want to exchange zy with yz, I have to do a new diagram and then smush things down and get to an answer. I don't think this is easy. Whoever tells you it is easy, they're a genius then. Personally, I don't think it is easy. Okay, so just to make sure, we go from 0 to 2 on the x's, from 0 to 5 minus 5 over 2x on the y's, from 0 to 3 minus 3 over 2 minus 3 over 5 on the z's, which is different than what we have here, totally different. Yet, if you integrate the same function as in example 2, and I think it's a good idea for practice to integrate this with respect to x, and realize that after doing all of this, you're still going to end up with 5 over 2, which was the answer for example 2. Okay, let's do this at least one more time. So we have the same tetrahedron. The equation of the plane is 10x, 15x. 15x plus 10y plus 6z equals 30. That's the plane. And you know the equations of the other planes. They are x equal to 0, y equal to 0, z equal to 0. Let's integrate. So the triple integral over this tetrahedron of a generic function with respect to the volume. Let's integrate with respect to what would be good? Let's do dx, dy, dz. Okay, so z will go only from 0 to 5. By the way, the one thing I did not finish in the previous, so by the way, we should have called this example 3. And example 3 is about rewriting the triple integral as an iterated integral in 6 different ways. So there's 1 way, 2, 4 to go. In those 2, dx was last. Now, in this new one, dz is last. So that is a different way. But what I did not mention here is when we integrate with respect to y, we get this triangle. When we integrate with respect to z, again, pretend this z does not exist. So we're still going from 0 to 2. So we project all of this triangle down to the floor, and we get a segment from 0 to 2. And that's one way to observe that we go from 0 to 2. I did put here going from 0 to 5 because the z can only go up to 5 and starting with 0. We're going to come back to that again, why it is from the other point of view of smashing the solid into a plane figure and smashing the plane figure into a segment. So we're going to move in the x direction. So pretend you are a spaceship here. When you're going in the x direction, what are you going to bump into? You're going to bump into this inclined plane. If you move towards us. If you move towards the away from us, we're gonna bump into 0. So we go from 0 to well, that's gonna be 2 minus 2 over 3 on the y's, boy, minus 2 over 5 on the z's. Yeah, so we can only go up to 2. But z can go up to 5. That's why we have that. So 2 minus 2 over 3y minus 2 over 5 is z. All right. Once the x is gone, we can project all of that, all of this tetrahedron onto the yz plane. And we're going to end up with this triangle, 3, 5. If you are a spaceship floating here and you want to move in the y direction, so you can go only up to here, we want to find the equation of this line and solve it for y, because we want to know the utmost y we can go to. The least y we can go is 0, but the utmost one is given by this boundary. So the equation of this in terms of as solve for y would be, so the most y can be is 3 minus 3 over 5 z. So 3 minus 3 over 5 z. You got to figure out the equation of this line and then solve the equation for y. And that is the most y we can go up to. Okay, once the y is gone, then project everything to the z-axis. And we end up with simply a segment of line. So again, smush this onto the z-axis and we go from 0 to 5. And that's why we obtain 0 to 5. So that is 3 down, 3 to go. Typically, it's not necessarily always. It's easier to exchange those two if you already have the last one. So let's do from 0 to 5. And now we're going to do dy dx. So, and the reason is because this picture is going to be the same, except that we're going to solve this equation for x. So the most x can go is 2. 2 minus, wait a minute, xy. Let me write down this and then decide. This is dy. Oh, no. We wanted to invert those two. Sorry about that. That's what is easier to do. Keep the dx as is, dx, dz, dy. Yeah, we want to invert those two because once we knock down the x-axis, we're still going to end up with this. All right, that makes more sense because I was actually following the x, but I'm sorry about that. So we solve this equation for z. Z can only go, solve this equation for z. So the most z can be is 5 minus 5 over 3 y. And then we solve this equation for x. X can only go up to 2. So the upper limit here is 2. Take away 2 over 3 y's and take away 2 over 5 z's. I'll tell you, this is not easy. Okay, let me double check this. So x has limits with y and z's, no x's. So whatever x is in the function, that's going to go away right away. And there's going to be only y's and z's. Z's are going to go from 0 to something with y's in it. So there's going to be only y's. Any z that was going to be in this step is going to be gone. And the only thing left is going to be y's. And then the y's are going to be gone last. So first, this makes sense. This integration makes sense. It is going to give us a number. So that is the first thing I want to check, because that is conceptual. I want to make sure the answer makes sense. It's like asking, what time is it? And if you answer, well, it's Tuesday, your answer is not making sense. Even though, by the way, today is Tuesday, your answer is accurate, your answer is not making sense. So we want to make sure that the answer at least makes sense, at least gives us a number, and it does. The next thing I want to do is look at the accuracy of the answer. So the x can go from 0 to up to 2 minus numbers, depending on how far we're on the y or on the z. If y is all the way out to 3, then we end up with 2 minus 2, 0. But at that point, z is going to be 0 also. Okay, so that's good. And then once we are in this picture, z can go up to 5 minus, the farther we go from 0 on the y, the less z we're going to get. And this makes sense. When y is 3, we end up with 5 minus 5, which gives us this 0. Yep. So this is accurate. Exchanging those two, we can piggyback on the pictures. If you exchange the last two, you can use this picture and this picture, and you're going to use this equation differently. And then we're okay. So that's 4 down. And then we have 2 more to go. This time I'm going to draw the picture on the left. Okay, so that's 2, 3, 5. All right, what do we have this far? We have dz, dy, dx, dz, dy, dx, dy, dz, dx. You know what? I just noticed something. I'm going in order in which I found this, dx, dy, dz, dx, dz, dy. In the first two, I exchanged dz, dy. In the last two, I exchanged the z dy, but I use the same general method, which means that those two are not consistent. When we get rid of the x, we have this picture. Let me go back very quickly. When here we get rid of the z, we have an x and y. When we get rid of, so this is xz. I'm going to pause so I can fix this real quick. Nope, the integrals are correct. I just, when I said I used the same method, I was incorrect. I did not use the same method. This one I copied from example 2. This one, I actually just redid it. This is a new, well, not a new example, but this is not necessarily using the same triangle of smashing when I came up with this. See, when we started example 2, we have a triangle that had a 2 and a 3 in it. This has a 2 and a 5. So this integral, the second integral we came up with in example 3 is correct. The first integral was from example 2, so that is correct. Not like it makes it correct, but I believe it is correct. The last two we did are correct. So no, I fooled myself. I thought I was doing something wrong, but no. All right. So we have x, y, z, y, z, x. I meant z, y, x. So z, y, x, y, z, x, x, y, z, x, z, y. Two more to go. So we can do dz, dx, dy. So that's another one we can do. Let's see. So the triple integral. Okay, so the last thing we're going to do is y. Y can go only up to 3. Then the one before that has to do with x. The first one has to do with the z. So the z would flatten, and we just have a 2 and a 3 involved. The z is gone. If we do z first, the z is gone. So we have this triangle on the bottom. Okay, and so we would be integrating x from 0, and the most x can be is 2 minus 2/3 y. 2/3 y. And then z, dz, dx, dy. So z goes up and down. Yep. And the most it can be is 5. Take away 5/2 x. Take away 5/3 y. So that takes care of this guy. So that is the triple integral with respect to z, x, y. And then we have one last to go, which would be dy, dx, dz. F dy, dx, dz. Well, z can only go from 0 to 5. Y initially can go from 0 to the plane, but we solve for y. And y can only go up to 3 minus 3/2 x minus 3/5 z. And then x, once y is gone, then we have 2 and 5. And x can go only up to 2 minus 5/2 z. Boy. So all of the 6 integrals are the 6 possible ways to come up with a triple integral. Some of them are going to be easier than others. And I do encourage you to do this. In our example 2, so this is the end. You know, the answer, if I was asking you for the 6 possible ways to rewrite the triple integral, those would be 2. And then we got 2 more here. And 2 more here. If we were integrating x, we should, in any of them, we would end up with 5/2, as we did in example 2. Which one is the easiest one to do of all the 6 of them? I think the one where x has to be integrated first, because that way the x So either this one or this one would be easier. And I think at that point, those two have the same kind of complications, the upper limits. So I don't think there's too much difference between those two. So why is that easier? Because that takes care of the x at once. If we have x, we will have x squared over 2. Plug in this. Yeah, we got to FOIL that out. So I don't know if necessarily that is easier anymore, because we got to FOIL that out. I don't know if there's necessarily an easier one to do. Do practice, though. And this is it for this video. Thank you.